Okay, so suppose we have 10,000 draws from a normal distribution, and we have some null hypothesis that says, well, that the mean of the normal distribution is 0, and we have an alternative hypothesis that the mean is greater than 0. Okay, and each one of those draws, we look at it and we say, well, it's an hypothesis. Does it come from a mean of 0, or does it come from a mean greater than 0? Okay, so we can calculate the p-values for each one of them. We take it and we just say, well, what is the probability of getting a larger value than the value that we got? Okay, and we can get a list of p-values, and we can draw an histogram of this. And as you can see, the histogram is with a density 1. So it means that it is indeed a uniform distribution. It looks very much like a uniform distribution. Yeah, it's almost perfectly. And we can also do this if it was a two-sided test. The only thing here is that we had to multiply the p-values by 2, because now it's a two-sided test. And so in each case, we take the minimum of the value greater than and the value smaller than. Yeah. So and we have to multiply the p-value by 2 for each one of them. Yeah, and we can see that even here the density looks like a uniform density. What happens when the null hypothesis is actually not true? So here we have that the random draws are actually from a normal distribution with a mean 2. Then in this case, you can see the p-values are completely not distributed as uniform. And this is because we calculate the p-values under H0, under the assumption that the mean is 0. Okay. Yeah, you can see this does not look like a uniform distribution. Okay, so let's take a sample where half of the hypothesis comes from the null hypothesis and half comes from the mu equal 2. Okay. And now let's see. Let's use the Bonferroni method. So the Bonferroni method, well, it just say you want that your alpha is 0.05. Just in order to control the family-wise error rate, just divide this alpha by the length of your hypothesis, so the number of hypotheses. And here we have 10,000. So this is what we will do. And we check for each one of them, each one of the p-values that we got, is it less than this stricter p-values that we got, that we calculated? And if so, then we sum all of this. This is our rejected group, yeah? And we also want to sum all of those only from the second group which we know is the true false. Yeah, this is the ones that we actually need to reject. Okay, and if we look at the number of rejections divided by the number of true discoveries, yeah, we get 0.008. Yeah, so less than 1% true discoveries. We had all the discoveries that they are true. Yeah, we had 5,000 discoveries that we could have made, but we made only 44 discoveries. Yeah, so the percentage is 0.8%. Okay, but how many false discoveries we made? 0. We made no type 1 errors from our discoveries. So you see, what Bonferroni does, it really narrowed the number of discoveries we made, the circle. And yeah, okay, so now it's the chance that you make a mistake is very, very small, but the number of discoveries you make is very, very small. Okay, now let's look at the Benjamini-Hochberg. So in R, the way you do it is you call p-adjust on your p-values and you set the method to be bh. Okay, and we do exactly the same as before. We sum all the ones that are below that we reject, yeah, for each p-value, each corrected, adjusted p-value by the Benjamini-Hochberg method that is below 0.05, we reject, and we sum all of this, and we get the number of rejections. And this is the number of rejections only from the true rejections. And let's see what are the percentage of true discoveries here. Okay, and here it's almost 40%. Yeah, so we moved from 0.8% to almost 40%. Yeah, so we capture a lot more discoveries now. okay, true discoveries. And what is the number of false positives that we have? Well, it's 0.03. So we did make some mistakes. Some of the discoveries we made are mistakes. Yeah, but notice that these mistakes are less than 0.05. In fact, we would expect to find 0.025 because we took exactly m0 divided by m is exactly half. We took exactly half true null and half false null. Yeah, but here it's almost 0.025. Okay, and we can also draw the p-values by indices, and this will be the cutoff value, but we can't see it very well here. So let's try to do a reduced graph. These are p-values of 10 hypotheses. 5 of them are from H null, 5 of them are from H1. You can see that if we do the Benjamini-Hochberg, which is just this, we will get 4 rejections and 6 non-rejections. We can see it also here. These are the p-values. Okay, you can see that up to here we are less than 0.05, but here we are already larger than 0.05, and I already sorted these p-values. And if I draw the line, it looks like this. Okay, so this is the last index which is under the line, and so all of the ones before it will be rejected. Let's take another example which will show us a bit better. Okay, this is how it will look. This is also the graph I used in the demonstration. And what will happen if I take away the smallest number? Well, if I take away the smallest number, you can see these two numbers are above the line. So only this p-values, this dot is below the line. So we will actually have a lot less rejections. If before we had 10 rejections, now we only have 5 rejections. Yeah, and remember, we only took the lowest number. So we would have maybe expected to get 9 rejections. No, if you take a very low number, you get much less rejections. What happened if we took the largest number? Yeah, if we took 0.06 out, okay, then now this dot is actually below the line, and all of our 11 hypotheses are rejected. Okay, so this is just to show you a little, give you a little bit intuition about what the Benjamini-Hochberg method does, and also how the Bonferroni method works. And yeah, so this was a pretty long video. I'll probably cut it to a few parts. I hope you enjoyed it, and see you in the next one.